position, well, what am I doing? So I can take C, I can take the final product of S with OS. Okay, so A is an ideal of OSS, which is our local ring, and I can quotient out by that ideal, so this is taking some sort of divisor of S. And then I can make the base change to C, so I can really pull back that divisor to C. So I gives me some divisor to be in C. And my claim is that this will then break into two pieces. So this is a slightly, like what I, like, the nice situation would be where you could say, oh, this has two irreducible components corresponding to V0 and V1. But that's not actually true. Each of these C0 and C1s is some union of irreducible components. So where each Ci is a union of irreducible components, and the points CS corresponding to vertices VI lie in C. So this is terribly confusing. Let me try to do an example. So here's over K, we're going A from B. So here's my S. This thing. There are two variables. Okay, so now I want to choose my partition. Well, I'm going to choose this to be V0 and this to be V1. Okay, so when I set A equal to 0, so set A equal to 0, so then remember that the what this means is that I have something like this. Oh, sorry, all the way around. And the local equation here is given by something like xy equals A. So then when I set A equal to 0, the local equation is just given by xy equals 0. And so it breaks into these two irreducible components. And so the idea is that along this edge, so this is xy. So when I set xy equals to 0, then these two vertices sort of break up. It turns out, well, this one also breaks into two irreducible components as well, but I don't care. I'm just going to ignore this. So I'm going to take the union of these two bits, and I'll take, well, this bit, which is still irreducible. So my C, so here's my C0, that's two irreducible components, and the C1 is still irreducible. Sorry, I feel this is not as clear as I would like. The truth is that writing down a completely formal definition of this thing becomes really painful. So I hope that this picture is sort of vaguely clear. So when you set one of the labels to be 0, then like on every edge with that label, your curve naturally breaks apart. And so the trick is to just sort of take the two, like
breaks apart. I think you showed at the beginning that you have an irreducible curve with a double point. So breaks apart is not really true then.
But notice that my edges always go between distinct. I'm only.
And now there are no loops. Yeah.
Well, I'm not saying there are no loops, but I'm only.
No, but these. Yeah.
These edges are not loops.
Yeah.
Indeed.
Yeah.
Yes.
Yeah. Yeah.
Yes. Exactly.
Okay.
But no. So yeah. So another good point. So the sort of the nice case. Suppose this had a label. Suppose this also had label B. Well, then I could say, you know, this just has two irreducible components, and I'll take those two irreducible components and they're what I want. But it can, of course, happen that there is just some other labels that happen to be A. And so this thing may not be irreducible, but okay, I don't care. I do this sort of breaking apart here.
But you are looking at a strictly local situation, right? We look at the closed point, we have this graph.
Yes.
So outside that, it is less singular, right?
Yes.
So somehow you're telling us what it looks like also outside
yes.
that closed point.
Yes, indeed.
But if you stay at the zeros of A,
Yes, exactly.
Yeah, so
So
those
somehow-
double points, they remain double points,
Yes.
and you don't know what happens with the rest of the graph.
Yes.
Yeah.
Yes, indeed. Yeah, so one sort of heuristic way to define the labels is that the label is exactly the locus where the double point survives in the base. And so, setting A equals to 0 is saying I'm only interested in the locus where these double points remain double points, but they don't get smoothed out. And so if they're actually double points, I can do my separating.
Yeah, so the two ends of the B edge, they could become one
Yes,
component.
indeed.
Right?
So so A is equal to 0, but as I move along, at the origin B is 0, but then B will become non-zero.
Yeah.
And so this node actually becomes smoothed out, which is why this thing becomes this thing corresponds to an irreducible component, because this node gets smoothed away. This node never gets smoothed away, so I get these two irreducible components which I just collect.
Yeah.
So the smoothing, you can think of contracting edges. Right?
Yes. As you can imagine, in the case where C is not regular, this gets it's a complete mess. It still works, but it's very painful to write it all down. Okay, so I have this C0 and C1, and these are things of codimension 1, right? Because certainly when I set A equal to 0, I get a divisor in the base, so it's preem, which is a divisor upstairs of codimension 1. And then the irreducible components of this divisor will again be divisors. So C0 and C1 are both divisors on C. So then C0 and C1 are both dividing on C. And we define divisor D for V0 to be C0. Well, and also therefore D for V1 is C1. But so notice that actually just specifying the set V, specifying the set V0 is enough to completely determine C0. So once I specified V0, I certainly specified V1, and then I've also specified A because it's the label that the edges go between them, so everything is pinned down. On the other hand, not every V0 gives me such a thing. So, V0 gives me a divisor if and only if all the edges from V0 to its complement have the same label. So this works exactly when all edges from V0 to V0 complement have the same label. Okay. So this is some rather brutal construction. It gives me a way to build divisors on my curve C. And now I specified my dt, but now I want to use this to build my d. So maybe it's good to understand what happens if I take one of these things and I put it back to t. Remember that I want to define, so I want d on C such that t upper star d is dt. So I started with the divisor dt, and I'm trying to sort of spread it out, build a divisor on C which pulls back to it. So let's quickly work out what happens when I pull back things of this form, because these are going to be my building blocks for D. So note that T upper star of div B0 is a Cartier divisor on CT, and the corresponding function. Okay, so Cartier divisors on CT, and it's certainly supported on the special fiber, so it gives me a function from the vertices of gamma z. What does that function do? Well, supposing my vertex is not in V0, then so it corresponds to a point over here somewhere, and so it corresponds to a point over here, so it's going to have multiplicity 0. So V maps to 0 if V is not in V0. Because really my divisor D does not come anywhere near that point. On the other hand, if V is in V0, then what happens? Well, you might sort of optimistically think that you get 1, but this is not quite correct. So because here we just took irreducible components, it's almost correct. What you get is odd vanishing on T of So you take this function a on S, you put it back to t, then it's a function on my discrete valuation ring, and it has some order of vanishing, which is some integer, and that's the integer that you get. This is a small calculation which, you know, one just has to sit down and do. But it's not difficult. And so now we're back to a sort of almost entirely combinatorial game, because we have this dt, this delta t, this function, sort of the function corresponding to dt, which is specified in a combinatorial way. And we also have these building blocks, and again, they give us functions which are specified in a combinatorial way. And so our goal is to find a collection of these v0s such that when I apply this procedure, sort of add up the corresponding functions, I get the function for dt, and then I know that I'm with. So maybe let me try to write this down a little more clearly. Let's call this function delta v0. Okay, so I'm given my delta t, and the vertices of gamma z. My goal is to find a collection of subsets containing the vertices of gamma. And I want such that maybe I'll call this condition star. Satisfying star such that delta t so this is ultimately what we need to do, and this is a purely combinatorial thing. But let me quickly explain why this is a good idea. So then define d to be the sum over I of ni of bi. So then t plus I of d equals dt, which is what we wanted. So this equality just follows from like plugging this thing in here. Okay. So this is what we want to do. So now this is really a purely combinatorial thing. And this is, so we still haven't yet used that our curve is aligned, and this is where we're going to use it. And again, the philosophy is that being aligned says that there are lots of subsets satisfying our conditions star. So if time allows, I'll actually prove this combinatorial lemma. But if time doesn't allow, that's not the end of the world. I think it's much more useful to do a couple of little examples. So suppose my basis polynomial ring are in two variables. And suppose my graph looks something like this. So I'm first going to do the aligned case. I'll do a non-aligned example in a second. So let's say the labels on here are all A, and the labels on here are all B. So this is aligned. And then I've got my delta t function, and so let's write down the function delta t, but I'm actually going to draw another copy of the graph on which to put my delta t. So this is the version labeled by elements of the ring. I want to make the version labeled by integers. I don't know what the integers are, so I'll just call them alpha and beta. And here I get alpha, 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 and beta, beta, beta. Now I have my function delta t. So I can always change my divisor by the pullback of something from the base, so I can always assume that one of the vertices takes value 0. And then my Cartier condition says, whatever number goes here, the difference must be divisible by alpha. In other words, this is something, this is say 2 times, I don't know, 2 times alpha or something like that. Minus 2 alpha. And then again, I don't know what comes here, but I know the difference is divisible by alpha, so this is, I don't know, 3 alpha or something. Again, I don't know what comes here, but the difference is divisible by alpha, so for some reason I decided that to be 5 alpha. And then here, this is difference is divisible by beta, so this is something like 5 alpha plus 2 beta. And this is something like 5 alpha plus 7 beta. The numbers are completely made up, but it will make the example work later on. So you get some distribution of numbers like this. Okay. So my delta t is the function written on this graph, and I want to try to write it in terms of these delta v0 gadgets. Okay. So the first thing I want to do is to take minus 2 times delta 2. So here I'm taking this at v0 equals v0, sorry, I should. Thanks. Now it actually makes a little bit of sense. So now 2 is the name of a vertex. Okay, so v0, I'm taking v0 just to be the second heading this vertex. Indeed, all the edges out of it have the same label, so it satisfies my condition star. I can at least define this thing. And then what is delta 2? Well, it vanishes in all of these vertices, and it takes the value alpha on this vertex here. So minus 2 times delta 2 is a fancy way of writing minus 2 alpha here and 0 everywhere else. And you can probably guess how I'm going to proceed. I'll do a similar thing here. I'll do plus 3 delta 3. And then this one, I have to think a little bit more because not all the edges coming out of here have the same label, right? So I can't just isolate this guy. But what I can do is I can isolate this chunk of the graph. And again, all the edges out have label alpha. So I'm going to do plus 5 times delta of 4, 5, 6. And so now I've got 5 alpha on all of these things and 0 everywhere else. I still need to arrange these things, but here again, all the labels, all the edges coming out have the same label. So I can just put plus 2 delta of 5, 7 delta of 6. Of course, this decomposition is not unique, and I mean, yeah, but so what? It exists. So in particular, then my d is given by minus 2 times div 2 plus 3 times div 1. So this is my recipe for my divisor d. And then by the sort of weird machinery I've been setting up, I'm guaranteed that this divisor has this pullback property. So this divisor defines me a section of this relative Picard space, and it lies within the closure of the unit section because it's trivial over u, because it's made of these sort of vertical pieces, and it goes through my point x. So that guarantees my flatness, at least around that point. Okay, so this is the basic principle. You do this sort of decomposition thing. Maybe it's important, let's see what happens in a non-aligned example to see where we're really using this.
Actually, you also got the uniqueness of this D up to bring back the divisors from the base. No? I mean, not from this picture, but already from the uniqueness part of the Neron matrix.
Yes.
So is that something that is also clear from the combinatorial picture here? Because you said there are many.
Well, here I just chose, as soon as I chose this one to be 0, I fixed the thing not to pull back from the base.
Exactly.
But still, I mean, I could as well have taken minus 2 times this set plus 5 times this set. And that's really a different kind of that's really just an artifact of the way I'm writing these divisors. I don't think there's a very intrinsic. Yeah.
So you are saying that it's not so clear from this combinatorics that you will always get the same D if you choose
I think
pick 0 somewhere. Or is it somehow by construction?
I think you will. I think the D will always end up being this. So yeah. So this decomposition will be different. I think the D will always be the same in the end. And I think you can see that.
Yeah, it should be.
Yeah, I think you can read it off, but
Okay.
I haven't tried too hard.
You can translate it in a potential problem, right?
Perhaps, yeah, I was thinking of
Or,
such a thing. Right?
yeah, but
of,
sort of
inserting current, extracting current.
Yeah, but it's sort of a potential problem with
Yeah.
colors, like with these different.
Yeah.
So it's a bit strange.
Oh, yeah. If it becomes with okay. Well, so not in. So indeed, the values are in an abelian group.
Yeah.
Yeah.
Yeah. Why not? Right. You can as well. Yeah, that's something new. Okay.
I'll do a non-aligned example. So here we can do a very simple thing. This is the easiest non-aligned. So the base is the same. K join A and B. And here we have label A and label B. They should be ideal, especially for ground right. I'm sorry. And then we're going to choose T such that alpha equals beta equals 1. So here's my S. I'm just choosing T to go sorry, it's a very unclear picture. S is the affine plane, and T just goes transversely through the origin. So this thing and this thing both give me multiplicity 1. So alpha equals beta equals 1. So my sort of graph with numbers on just looks like this. So then I can do anything I want. Put 0 and 1 there, for example. That would be a Cartier. That would sort of satisfy the conditions to be a Cartier divisor. But it's clear here that there are like the only V0s I can take are the empty subset and the whole thing. Like, there are no non-trivial V0s that there exist. Okay. And so that's why being aligned is important. Okay. So now I've got 7 minutes. I don't want to, I mean, proving this thing is a bit of a, but let's write down what do we need to prove. What we need to prove is, okay, so we have some graph and the edges have some labels by some sort of set A's and B's and C's, say, and then these have some orders, alphas and betas, and then I have some collection of numbers which satisfy this divisibility criteria. And then the claim is that I can always write this collection of numbers as a sum of these sort of delta V0 type functions. So this is now a completely combinatorial thing, and it's really moderately annoying to prove. Let's give a sketch of a proof. So what you can do is you can decompose the edges of gamma by, say, E1 equals E2, if and only if E1 equals E2, or there exists a cycle gamma with E1 in gamma and E2 in gamma. So a fun exercise is that this is really an equivalence relation on the edges of gamma. So this gives me, so once we've done the exercise, this gives me an equivalence relation on the edges, and so it really breaks them into sort of pieces. If you're used to decomposing your graph into bridges and two edge-connected components, this is a bit different. So bridges will always be, like a bridge in your graph is always its own equivalence class. But if you look at what happens here, for example, then even though this is two edge-connected, this is an equivalence class and this is a separate equivalence class. It's really an equivalence relation on the edges. So but it's a thing you can do. Okay. And so aligned says that E1 equals E2 implies label of E1 equals label of E2. So that's just a rephrasing of our alignment condition. And so what we can do is, let's now draw sort of a sketchy picture of our graph. So notice that, so these give me sets of edges, but I can think also about the induced subgraph. So the smallest subgraph which has those edges, just put in the vertices necessary to turn it actually into a graph. And then I can really start to sort of draw this thing. These subsets will always meet at exactly one vertex. So I'm breaking my graph gamma into these sort of blobs like this. Some of these blobs will just be like single edges, but okay, it looks something like this. And this sort of has a tree-like structure in the sense that, well, I guess you can, if you want to make a graph by putting a vertex for each of these things and edges between them, and then this thing is actually a tree. Because imagine if you have something like this. This is very bad because then actually you can find a cycle in your graph which goes all the way around there. But that's sort of contradicting the partition that you just defined. So this kind of thing is not allowed. Okay. And so we use this sort of tree-like structure, and now what we want to do is we can say, well, we can always assume that we have a 0 somewhere, so let's put it there. And now I know all of the edges in this bit of the graph have the same label. So what I want to do is, so for a vertex out here, well, I just take it on its own, and I take this to be my V0, and I put the relevant coefficient. So this would be one V0. But supposing I have a vertex here, which connects onto some other part of the graph with labels A and B. So here, again, I want to choose some suitable set V0, but this is the set V0 that I want to take. I want to take all the rest of the graph. So more formally, what you can do is you can define a function from the vertices of gamma to the vertices of this component of gamma, and you send a vertex to the first vertex that it hits there. So for example, this guy will map to there, and this guy will map to there, and then you define V0 to be the preimages of this sort of contraction function. And then by suitably choosing by choosing the coefficients, like by choosing the coefficient to be exactly what you want here, then you can sort of arrange to have zeros in the whole of this component. So you can do sort of, by subtracting off suitable ones of these, you can get zeros everywhere in this part of the graph. But then you can just say, well, you can just move on to the next bit of the graph and say, okay, well now I've got a 0 here, so I just play the same game here. And to write down the proof formally is slightly annoying, but it works. So I'm actually kind of happy with this argument because you can really write it down correctly in like a page or so. And this is in the regular case. In the paper I wrote, I did the case where the graph isn't regular. And then it's several, it's a good couple of pages longer. So this is you get a nice simplification in the regular case. Okay, I think it's a good time to stop. Are there any questions, you think? Everything was so clear that everyone understands everything, or so unclear that you can't? Yeah, who knows? It's always the question.
So you don't think of this in terms of a potential problem?
I mean, no, because I mean, at some point it's just this sort of, I don't know. I'm not sure how to translate it into how exactly to translate it into a potential problem. I mean,
well,
it's just this random decomposition.
No, but the problem you have to solve is, I think, you can put you want to make a divisor that has certain degrees on all the components itself, right? So if you were over a discrete valuation ring, then it would be given by this intersection matrix. Mm-hmm. And that's a Laplacian, right?
Yes, indeed.
That's
Yeah.
So there, but
I think you were doing it.
But I think you calculated for us the effect that what you can do if you can. I think if you have a point, well, you gave examples. So I think you get similar things, but not with numbers, but with labels.
Because this Laplacian is a map from Z to the V to Z to the V, so to say. But now on your vertices there are still numbers, but on the edges you have, well, labels. So
so you have restrictions in this game, I think. You are only going to use points where all the, well, if you want to use a point, it's a point where the labels of the outgoing edges are all the same. So it looks like the same game, right? You really do this game because you have more restrictions.
But somehow I already know that my like the delta t I start with indeed is this Cartier. Like I start by assuming the situation over DVR sort of has already worked out.
Yeah, but here you prove one direction, right? You prove if it is regular and aligned, then we have a Neron model.
Yeah.
Then your closure of the unit section is flat.
Yeah.
But I think you also do the other direction. If the closure of the unit section is flat, then something happens. And for that direction, maybe you need something.
So that would be really, I mean, at the moment, it's really, I just do pages of like horrible hands-on combinatoric stuff. But if there is indeed a nice way to, I mean, so I use like, sort of max cut min flow in graphs with labels in groups and stuff. But if there's some way to just say, to write it as a potential problem.
But I thought that you could reduce all these questions to questions over DVRs by taking test curves in the base and looking.
But this is sort of the opposite. This is really not something you can reduce to DVRs, because the whole point is to do the...
Yeah, but to show that the closure of the unit section is not flat, you can take test curves in the base and see what happens.
Yes.
Because then if you see that the closure of the unit section has positive dimensional fibers over the base, then it's not flat.
Yes.
Right? And that you can do.
So I don't know how to prove it like... So what I prove, to prove the converse, I prove that this D can't... I construct the same delta T, and I prove that there does not exist a D satisfying all this stuff.
Well, we can discuss this.
I mean, I would try to do this positive dimensional thing, but I could not get it to work.
Oh.
I mean, I know that that's what happens, but I don't know how to really prove that the dimension was positive. I couldn't see how to do
things.
that?
Well, if you take there your T,